last. And we'll go. Oh, Ariel, go ahead. You have a question.
Yeah, I was wondering if it would be possible if our project could maybe be a partner project.
Do you already have somebody in mind or something? Or
Yeah, I just feel like I looked at it and like I was like playing around with it and stuff, and I'm just like not tech savvy.
Mhm.
And so it was just kind of hard. Like, I mean, I need to keep trying and stuff, but
Personally, I mean, well, so here's, I guess you could, my take on that was probably you could probably do something similar with each other. At least you could work on it with each other and do different things. But I don't necessarily want to just split it up so that some people are doing a whole one and some people aren't. But I'll be here, like if you need. I still have MJC classes on Tuesday, which I'm kind of turning into office hours. So if you guys want, I'll be able to hang out with you guys and can show you, like, if you need tricks or tips on things to how to do the tech part of it. I've been more than happy to sit with you and go through it. Once you do it a couple of times, it gets easier. And so I just like to work through it with everybody to make sure that we can do that. Let me see here. Somebody says, oh, so somebody said, ask when is it due again? So I'll get back to you again, Ariel, in just a minute here.
okay, thank you.
Um, sorry, just my brain flits when I see things. So the due date then would be that week or let me see. Well, before I say anything, let me just go back and consult what we got here. All right, so the final project instructions, if you click on that, let's see here, right there. So it's going to be, the rough draft is due that class. So the next class, basically, we're going to do a quick little run through. The first part of the class is going to be when we come back from break. So that's 2 weeks from now, right? 2 weeks from now, where you guys will do that first little peer review part of it. And it's gonna be a rough run through, a rough draft of it all. And we'll give that tag feedback, all that positive feedback for everybody to, just polish it up a little bit here and there, make a few changes, listen to some suggestions, and then we'll present it for the end on that final project day. I mean, the final, what do you call it? Finals week, that last class of, when is that, the 16th or something like that? I can't remember. Let me look at the, oh, I'm not even sharing my screen, am I? Let me say, there we go. That would make it a lot easier to see things. Sorry about that. Let me know if I forget to do those kind of things. So yeah, and oh yeah, calendar. Yep, so that'd be the 10th, right? So the 10th is like the final due date, but the third, 2 weeks from now, is when we're supposed to have that rough draft. Now, here's the other thing. So getting back to Ariel's comment is, the whole idea of this is to not, it's not to cause stress or make people panic or do anything like that. It's to get us a little bit better working with some of these tech tools that, especially if you're going to be like teaching and things. Okay, thank you. There's going to be lots of times where you're going to have to create and work with things for students, especially as we move forward here. If you're going to be a teacher, or if you're not, there's going to be lots of times where you need to use these tools to perhaps present, to make a case about something else, right? Whether it be your job or something like that. So that's the whole goal and the purpose. And really is also to give you guys a better sense of our place in the valley and where we live, or whatever you choose to do for your final little 5 stops there. That's something that I think is a very important part of the education, is kind of giving you the ability to look and choose and talk about it. Now, if you guys want to work with each other and have like study groups, or talk about doing this or that, that's fine. I don't have a problem with that. Because you'll be helping each other out on how to place things. You're going to be doing that like peer review anyways. I would just suggest, whatever you want your trips to be, if you're going to work together on that, then, like find 10 stops or something like that. And then you can do half and they can do half or something. something in that neighborhood. All right. But ideally, like really, once you get the hang of this, my whole goal for the whole project was to not take more than like 2.5 or 3 hours total, to kind of put together and do all those things, with 5 different stops. So, just try to find 5 interesting things that you think is cool, state parks, whatever. And if you're having, and that's another thing, if you're having a brain block on what you might want to do it on, then feel free to meet with me or send me an email or something like that. And like I said, on Tuesday, I'll have kind of pseudo office hours if anybody wants to bounce ideas off or something like that. And we can help get you unstuck if you're feeling, not super inspired or anything like that. So I can help with that. But that I guess that's kind of the long answer for, I'd like to see everybody do their best and turn in their own individual projects, but I got no problem for people working together and talking about it. And I mean, I highly encourage you. I hope you see this class by now as to be collaborative with one another. And so maybe by working with other folks and bouncing ideas with other folks, you might be able to come up with some ideas that could expand on whatever thing you're thinking about. Does that help a little bit, Ariel? I mean,
Yeah, I was just like kind of stressed because like this is an online class, so like I wouldn't get to see you and like talk to you if I needed like extra help,
Well, and so you can, I mean, we have, well, obviously next week is, I mean, except for Tuesday, I'll have like office hours, or I think it's like at 1:30 or something like that. And I can send out, if you guys contact me or whatever and want to meet, I can give you specific links for that. But I'm trying to be available. So Wednesdays, I don't have classes on Wednesday. I have other commitments and things, but I can clear some of those off on Wednesdays if anybody needs to meet. And remember, this first time through is just going to be a rough draft. So it's not like the end of the world or anything like that. And this whole project is the first time any of us have probably ever done this, or any of you guys have probably ever done this. And so I totally am, taking that into account, where we're trying to be encouraging and make it fun and make it a positive experience. That's the whole idea here. Yeah, but I'll be around if you want to, if sort of around, but if you email or reach out to me before class starts, next on the 30th, what is that, the 30th or something like that, I can probably hop on and we can figure out a way to communicate via Zoom, just like we're doing now, and show each other, how to help with some of these different things. So if you need it. So I'm here to help, I guess, is the main summary conclusion here. But so hang in there. You guys are doing great. I mean, you guys are doing awesome. And that's pretty much what I got to say about that so far. And I'm looking forward to see what everybody can produce. My goal here too is, hopefully that nobody, unless you have to this vacation, like just step away from things, go be with your family, friends, whoever, and do whatever you need to do to just kind of recharge, right? And then hit the ground running those last couple of weeks. Everybody needs it. We need to put our feet up for a little bit. I'd never really want to ask people to do anything over a break or anything like that. So if you have the time, you can work on it. If not, there should still be plenty of time, even when you come back a week later, right after classes. So trying to give everybody as much flexibility and wiggle room as possible here.
Professor?
Yeah, go ahead, Sarah.
Quick question. Is there a class on Friday after Thanksgiving?
No, next week? No.
I was confused. I thought there was. Okay.
No, I don't think so. Let me double check the Stan State Stan State academic calendar. So you can see I'm not super great with calendars because it's like the first thing that pops up in my Google search. But yeah, Thanksgiving holiday, campus closed 25th and 26th, obviously. So no class. Let me see here, 25th, 26th. Yep. So no classes all next week, basically. That's how.
Okay. Thank you for clarifying, Professor.
Yeah, no worries, because I get confused on calendars and things like that too. All right. So let's get going. I got some cool things to show you. I think tonight, I got a few little fun activities for everybody to do, and we might have a chance of getting out a little early as well, and so you guys can continue about get an early start on your holiday ideas and vacations and things. All right. I'm trying to breathe here. I've been apparently suffering from some high blood pressure as of late. I don't know what could ever be causing that. But if you hear me have a little bit of a shortness of breath, that's don't worry, I'm okay. I don't have COVID or anything like that. I'm just trying to get a full deep breath, hypertension, and don't worry. All right. Worry if all of a sudden I pass out and I'm not on screen anymore, but I don't think that's gonna actually happen. But anyways, all right. So what are we gonna do today? Keep on keeping on. You guys have been doing great. I think we talked a little bit about that. We'll talk about atmospheric dynamics, and we're gonna start building some evidence to understand why the Central Valley has such kind of hot and dry summers. And we're going to tie up all this information that last week here when we come back, right, from classes. You know what, I'm gonna go back. I just had a thought now with this academic calendar. Yeah, finals are the 13th through the 17th. Last day of classes would be the 10th. Okay, yeah. So now I'm trying to think here. So the 17th. So I guess our final would be the 17th. Okay, that makes more sense. So you'll be able to do the rough draft on the 3rd, and that'll still give you 2 weeks after we do the rough draft to then do the final bit. So sorry about that. It just kind of crossed my mind. What screws me up is MJC and Stanislaus have MJC's out a week earlier than Stanislaus, and the two classes get cross-wired in my head sometimes in terms of who's where and when we're done. So, Ariel, go ahead.
Sorry, one more quick question.
Yeah,
On the sketch notes, if it doesn't say to have a sketch with it, does that mean just like the definition part?
Oh no,
or,
so always with the sketch notes, like the sketches, I always kind of want to be the sketches are kind of the main thing, and these are just kind of the ideas to go around those sketches is what I'm talking about. So like for this part tonight, we'll be looking at the Bernoulli balloons and things. I'll be sketching with you to show you some ideas for some sketches. But yeah, for the most part,
on the one before this, the big idea on the 12 for like the ice sheets, and like what are they in the alpine glaciers, like are we drawing something for that?
So for this one, you can basically all of these things, the diagram of the alpine and valley glaciers, you can kind of probably fit in like with this, and then just tell me so for this one, the sketches you don't necessarily need, it's just what are they and where are they? And then you have diagrams down here to kind of fill in those blanks. So like, where would you find ice sheets? Where would you find alpine glaciers?
And then, sorry, one more. And then on the week before this,
okay,
on the porosity are we drawing a picture of that? And then the infiltration and runoff breakout, are we doing images of those?
So yeah, the breakout room, just some of your quick ideas. So yeah, which types of so just a quick little sketch to at least illustrate one or two of the things you witnessed for that one. Yeah, for sure.
Okay.
Yeah, that's a great question. And then for the porosity and permeability, there are a few little sketches that show like grain sizes and how they're compacted together or spread apart and things like that. That'll get you started on that.
Okay, thank you.
Yep, no problem. Oh my gosh, sorry about that. My nose is itchy. Okay, so a couple of things. The geo noses then for you to geo noses. This last week, it was so the 15th. What's today? The 19th. So 4 or 5 days ago, British Columbia and Washington had just a really massive atmospheric river, a true Pineapple Express coming from Hawaii, full of atmospheric moisture, and just hosed British Columbia and Washington. Some of those places got over 220 millimeters of rain, which I think is in the neighborhood of, let me see. That's in the neighborhood of about 9 or 10 inches of rain in just a short period of time. Some places actually in the mountains got upwards of 15 to 20 inches of rain. And all of that caused huge amounts of destruction in terms of flooding and landslides. And I'll show you a few pictures of that in just a minute. But the reason I really want to show this to you too is, this is some of the same places that just this past summer set world records in terms of largest divergence from actual average highs for that time of year. So they recorded 121 degrees up here in Lytton, Canada, which is, one of the hottest places, on Earth. And it was crazy because, I mean, their average temperature for that time of year is like 20 degrees Celsius. So it was like basically twice as hot as it normally would be in terms of Celsius up there. And then just a few months later, right, in the wintertime, wham, they get smashed with that atmospheric river. And same thing happened with us, right? We had experienced pretty hot, dry summer here as well. And then we had the early, or the kind of mid-October smashing of rain as well. And now we've hit this dry spell. So this is what we refer to as climate whiplash or weather whiplash. That's part of climate change here, where we just go from one extreme to the other with kind of nothing gentle in between. And this is what a lot of computer models are showing and suggesting will be kind of the norm as we move forward here under some of these climate change regimes. So we will be taking a look at, and that's what we're starting to build today, is understanding the structure of the atmosphere and understanding how, all of these storm systems kind of move throughout, and then how carbon dioxide and a few other gases are affecting those atmospheric properties, the thermal properties of the atmosphere, and what we can do about it, and how we can there's still plenty of time to avert, major catastrophes, but we got to start doing things about it. And that's hopefully what we'll end this year on, is giving you the ideas and the means necessary to become informed people, to, help promote and do what needs to be done to, basically stave off things that would be bad for human civilization globally. All right. And remember, it probably is not going to affect us as much as many other countries in the world that have not done anything or very little to contribute to the climate change gases in the atmosphere. So this is an aerial image, a drone survey of one of the towns in Canada. This is Abbotsville in Canada. And what's so really weird about this, and you can kind of see the street houses and stuff like that, and ranches and big farms and things. This is in British Columbia. This valley here was actually, up until the late 1800s, it was a big lake. So the lake here that you see now was a permanent fixture up until about 120 years ago or so, the late 1880s, where they decided to straighten out the river and make a canal and divert it around the lake and make it come back down around this way in order to basically drain the land and make it farmable. Well, like we learned earlier this year, Mother Nature is kind of taking its course, and it's winning. I should say they drained the channel like this and started making it go that way. And then this one, there's supposed to be a levee and a canal, and it drains to the north of the picture there. I was pointing the wrong direction. But just some things to take a look at. If you want to look, you can just look at like Abbotsville flood and things like that. Oops, come on, go full screen. Here we go. So this is what it looks like in the air, and there's still tons of cities up there underwater from all these floods coming in. There's been huge, massive landslides and all sorts of nastiness that have happened up in the Rockies up there. And this just happens to be kind of a low basin that is filled up. And, it's kind of a warning shot across the bow here of how are we going to plan in the future for bigger floods like this. And California is going to have bigger floods like this. That's what the models are showing. We've already seen some examples of that. So we need to offset our levees and give the rivers more room to flood and let it soak in so that it doesn't affect the infrastructure. We got to give the water some place to go. And even if we were to build like a whole bunch of dams and things like that, it's not going to hold all of that back. All righty.
Professor, quick, sorry to interrupt.
Oh, sorry, go ahead. My volume goes down. Go ahead.
I just have a question. So
Sorry.
so the models are showing we're going to have like floods and stuff, but so the dryness is not So we are going to get rain eventually then.
So yeah, and then that's the weird thing, and that's what we'll be talking about towards the end of the year too, is some of the last little bits, or not the last, but the most recent bits of modeling and data suggests we're going to have more of these extremes, where we're going to have the extreme heat and the extreme dryness. And so that means even when these periods in between rains, everything is going to be so much warmer that it's going to cause a lot more evaporation. So when we have droughts, the droughts will be worse and more severe just because the evaporation rates are much higher, and causing that to basically suck more water out of the ground when plants are trying to grow and things like that, or you might need more water to water crops. And sometimes it's so much that, you know, it's just not monetarily efficient to keep farming in some of those regimes. But when we do get rain, what a lot of the models are suggesting is there's a higher probability of having larger, wetter storms coming through, so that when we do get rains, the likelihood of having a stronger, more kind of a rain that gives us way more than what we would normally average in a given year, or over a period of a year, we'd have much more of those bigger storms flying through. And I have the data. We'll be taking a look at those data in those journals at the end of the year. So what's kind of weird in California is it looks like in California specifically, the models are suggesting we may end up with just a smidge more rain, a smidge more total precipitation in California moving forward under the current kind of moderate levels of climate change that we know is going to happen no matter what we do right now. And what's kind of interesting about that, I just lost my train of thought here. What's interesting about that is we are going to well, no, I just lost my train of thought. Give me a quick second. What was I talking about? Oh yeah, the floods. This is what Friday nights look like, folks. This is what Friday nights look like, I guess. So there's a higher probability of having more intense storms coming through. And so we're not going to get as many, we may not get as many of the kind of lighter, gentler rains, but we'll go longer between periods of lighter of rain. And when we do get those rains, they'll be much higher in volume than just kind of having a whole bunch of small storms. So instead of having a whole bunch of small storms, that's the best way of me trying to put it. Instead of having a bunch of small storms over time, you might have one or two big storms in a short period of time that dumps the same amount of water as those little storms over time, but it's in such a short amount of time, it's not enough for things to infiltrate in. It creates more runoff, it creates more floods. And the big difference is the elevation of the snow levels are going to be much higher. So a lot of that is not going to be as much snow in the Sierras as we normally would have in the past. And it's going to rain higher up. So there's going to be much more runoff and not stuff holding into the mountains as snow until the spring. So those are some of all the things to look forward to. And that's what kind of happened here is when the rain that came, oops, I'm trying to mute this. The rain that came was very warm because it originated from Hawaii and it melted a lot of the snow on top of things. So it melted the snow, it had all the rain as well. And that just flashed all the river down. It caused all the erosion of all these different bridges and things. There was for a couple of days, it's like 5 or 6 days, some of these towns in inland British Columbia were completely cut off. All the roads had to go over rivers and the rivers washed out all of them. And so they had to helicopter some folks out and they did some quick fixes to basically put dirt across here so cars could get out. But yeah, it's going to be a multi-billion-dollar disaster. And that doesn't even count all of the amazing like landslides and rock sites further up in the mountains and things like that. So yeah, I mean, it's interesting times, right? It's just kind of like one of these precursors to come, and it's happening up here. It's gonna eventually happen down here. So we can prepare for it, though. We can do things about it. We can manage this. There might be some tough choices having to be made here and there. But it can be done. It can be done in an equitable way as well. And that's what a lot of, scientists are working on now, is using social constructs to be able to figure out how to do that and how to do it successfully. I just wanted to show you this really fast too, but I kind of got off on a little tangent here. The weather, there was hints and signals of maybe some rain, maybe whiffing through on Tuesday and Wednesday. But for the most part now, it looks like we're still going to have not much rain for the foreseeable future here. So November was pretty doggone dry, considering we had that really good burst of rain in the middle part to end of October there. So anyways, just something to think about and talk about. So before we can understand how we have all of the climate change happens, and the effects of the atmosphere and the effects of the climate on different places in the world, we need to figure out some of the set the ground rules, I guess would be a good way of saying it. Set the ground rules of how does the atmosphere work. And we're going to kind of concentrate on our Central Valley part here that's going to be built over the next 2 weeks. So by the end of tonight, we're going to start gathering some information that helps basically put some background knowledge in our brains. And then next week, we're going to start applying, or the next class, I should say, we're going to start applying all of that to figuring out this question of why is it so doggone hot and dry in the Central Valley during the summer. All right, so that's what we'll be able to answer towards the end of this. And that's kind of what we were looking at here. So without further ado, since we're going, since you guys asked a lot of good questions earlier, I'm not gonna have you sketch this, but I just want you to think about this before we move on. All right. So, right, air is all around us. We don't think about it. I mean, the only time I think we ever really think about air is when we can see it, when it's like really polluted and it looks pretty terrible, or there's smoke coming in from wildfires and things. That seems to be about the only time you think about it. Or maybe you think about it like me when you're a little kid, or maybe you still do it driving. You're driving, you roll down your window and you stick your hand out the window and do the aerobatics like thing, the aeropalmatics, or you're driving too fast, you stick your hand out the window and your arm goes the other way. That's when you can feel some air, or when it's windy and things blow down. But a lot of the time we just take it for granted. It's invisible. We don't think about it. We don't see it. So I just want you to think, if you could put on like a magic pair of air glasses that allows you to see the air molecules around you, that could, like zoom them in or zoom into them so you could see them and see what they're doing. My question to you is, what would you see? All right. So you don't have to answer that to me. I just want you to think about this. What would you see? What would those molecules be doing? How would they be moving? And we're going to do a little bit of an experiment here and some drawings in just a minute to show you maybe some ideas that could help answer these questions. All right. So hopefully one of the things to think about too is air is a gas. And so gases, remember, they fill up. High school chemistry, junior high chemistry, gases fill up their containers. They're all around us. There's air bouncing around the room. That's the room that I'm in right now. It's bouncing off a wall. When I'm talking, I'm blowing out air, and then it's bouncing off things, and some of that air is bouncing back in my face. That's how air moves. And knowing how air moves is kind of important during COVID too, right? To understand how those aerosolized particles move around up there. So if you're thinking about that, like, okay, what would it look like? How would it move? Let me give you a small little bit of idea. And you might not even realize what in the heck is in like just dry air. So if I had a box that was like this, a cubic meter of air, all right, a cubic meter of air. And I think Danielle would probably recognize what room I drew this to represent. This is my old classroom at the high school. That's kind of what I'm showing here. And so if you have this room, I thought it was a good room to draw, so I drew it. If you have this room, what would it look like? What would the air be doing in there? Well, if I had a box of that air that was about 1 cubic meter, or about the size of a dishwasher, if you have a dishwasher at home, that's about a cubic meter, somewhere in that neighborhood. If you open up that dishwasher inside, this is how many molecules of air there would be in there. All right, I don't even know how to say that many numbers of zeros. Like I just know that's millions, millions, billions, trillions. I have no idea what you call any of these once you get past that number, but just in there, that's a lot. So think of all of these molecules. That's just in one dishwasher size. Now imagine your whole house and all of them bouncing around with each other and interacting and smashing off your forehead and bouncing off the computer screens, and then flying someplace else. They continually mix and they go all over the place. And we're going to learn some of the things that dictate how they move a little bit later. But if you were to take a breath of just pure dry air, right? So no pollutants in it, no particulates in it or anything like that, just the gases of the air alone, it's mostly made up of nitrogen. All right, mostly made up of nitrogen, 78% nitrogen, about 21% of the oxygen. So when you take a deep breath, right, 21% of those molecules that you just breathed in are going to be oxygen down at sea level. All right, for sure. And even up higher, it's still going to be about the same percentage, just not as much of it. And then about 1% argon. And then look at this, carbon dioxide is like not even, it's 4/100ths of a percent. So that's like 0.0004 parts per million. And I'll show you what that looks like in just a minute. But it's a really, really small fraction. But this small fraction plays an outsized role in our atmosphere moving forward. One of the things that maybe you guys have ever noticed that can make air visible sometimes, if you've ever driven up into the mountains with a bag of chips, like this, the chip bag can kind of expand. And the reason it expands has to do with lower air pressure on the outside up high in the mountains versus higher pressure from where the bag was packed on the inside. So those molecules on the inside under the higher pressure are exerting more of a force and pushing out, and makes those bags inflated like this. If you go over a really high mountain pass, sometimes they'll pop and can give you quite a fright if you're not prepared for it. Or the opposite can happen if you take like a drink of Gatorade or a plastic, really like a thin water bottle like this or something, and you take a drink of it up high in the mountains, and you close it and you forget about it, and then you drive down to the valley and the bottle is all squished because the higher air pressure down here squeezes the bottle that is full of lower pressure mountain air. So why is that? Well, we're going to take a look at that, and we're going to draw some pictures here in just a minute. So we're going to do this little one. It's called Bernoulli balloons. Basically, instead of balloons here, I had 2 tennis balls hanging around when I made a little video for this class last year. So I want you to make a prediction. If I had 2 balloons that were hanging on the string from a stick, and somebody blew pretty forcefully in between the 2 balloons, in this case, I have tennis balls that you'll see in the video, what do you think is going to happen to the balloons? All right, I want you to think about it. What direction will they go? Will they stay the same? Will they move apart? Will they move together? Will they kind of move back and forth? So I want you to think, I want you to make a prediction here, and then I'm going to show you this quick little video, and we'll see what happens. All right. And tennis balls are a little bit harder to do because they have more mass, but it works. Let me share my sound. So hold on. There we go. I'm going to make them so they don't move too fast, and I'm going to blow pretty quickly between them. Let's see what happens. So, is that what you expected? Works easier with balloons if you can find them laying around your house. I didn't have any, so we used. So this tennis balls, when you blew between them, that first initial reaction was for the balls to come together. They didn't go apart. They didn't go side to side. And this is kind of one that usually kind of trips people out. They're like, what? I didn't expect that. Why is that happening? Well, let me show you. So let me change my screen. There we go. And I got to get my, where'd my pen go? Oh, here it is. I put my pen where it's supposed to be, and I had a hard time finding it because I organized it. It's much better to not be organized. I find things easier that way. I'm actually pretty darn organized, but okay. So here's the before. There's the tennis balls that we were looking at. So here's my first little sketch, and these are some of the sketches you can think about for your sketch notes and things. But what I'm going to do is I'm going to draw and represent air molecules as these little blue dots right here, okay? And I'm trying to represent here that these blue dots are equally all around the little tennis balls here, like this. All right, so let's just pretend we got all those around there. And remember, all of these little, let me go to this, sorry. All of these air molecules are consistently and constantly bouncing off and going in all and just kind of going in all different directions, back and forth and up and down. Sorry, my screen was a little shaky there. So it's kind of moving back and forth like this in all different directions. The result of all these gas molecules bouncing around so randomly like this is that sometimes, or a lot of the times, they'll end up bouncing into the tennis balls, but they end up doing that basically equally in all different directions. So the air pressure, what we can say is before, the air pressure is being exerted equally on both of the tennis balls here and from all directions. So it doesn't matter where or which direction, underneath or on top of the ball, it doesn't matter. We have air kind of equally pushing on all sides of it. That's how air pressure works, right? So then the after part, how did that work? Well, we saw that these balloons, or the tennis, oops, wrong one. We saw that these tennis balls came together here. So I'm going to try to draw two tennis balls that have come over here. Whoop. All right. So what's happened here in this case is we've had, for some reason or another, the balls have swung towards one another. Actually, I'm going to erase this just a little bit, and I'm going to make it so it's not quite hitting, but it was on its way to hitting, just so I can better illustrate what the heck was going on here. Actually, I want to keep the same perspective. Hold on. There we go. We'll do it like this. All right. We'll do it like this, and you can see that it's starting to swing over this direction, and this one was starting to swing over in this direction. So why is that? Well, we have to go back really quick to our little air molecules. So the amount of air molecules on the outside is going to pretty much stay the same on the top and the bottom and kind of all around right here. But what's different compared to this one is when we blew the air this direction like this, what ended up happening is we took the air molecules that were in here and we've basically blown them out and we've gotten rid of them. They've kind of, all those air molecules now, we've given them a certain direction, we've gotten rid of them, and all those little air molecules that were between the balls that were helping to exert this outward pressure over on the befores, we've basically gotten rid of them. So there's not as many air molecules pushing out, and you have way more air molecules kind of pushing in from the sides like this. Okay, so we have these extra pushes here, but there's hardly anything pushing back. There's like maybe one or two molecules pushing back, and it's a weaker force. So basically it turns out there's greater pressure on the outside. So I'll just say greater pressure, and then I'll just say in here would be, let me get it so you guys can see it. I would say this is like low pressure. So when you're blowing, when you blow through, that creates low pressure. You're blowing these air molecules out that were between the two tennis balls, and that allows higher pressure still pushing on the outside. Since it's higher than the low pressure, it causes the balls to kind of smash together here. All right. So that's the first part. You can try this at home. Just get two balloons or something like that. The easier one you can probably do at home is this one, which is kind of the $1 million challenge. And it's a pretty fun one where you just need a couple of books and you need a piece of paper, like a flat piece of printer paper. And you put the printer paper over the top of the books like this, and you challenge somebody to blow this piece of paper off of the books. And as long as all four corners of this paper are completely on top of the books, well, let's see what happens. Is it even a possible challenge here? All right, so that's what we're going to take a look at. Let me share my other screen. Sorry. There we go. So like I said, here's our books. And if we if we take our books and we put a piece of paper on it and we try to blow underneath this or try to blow on top of it anywhere, what do you think's gonna happen to the paper? Is it gonna blow off? Is it gonna stay put? Is it gonna spin off? You know, just I want you to think about that. Think about it in your head really fast. And then I'll show you the diagram here. And in this case, this is all I had around sitting in my office last year were these goofy boxes. But if you can get textbooks that are the same width of the paper, that would be great. And you can try this at Thanksgiving with your family. And if you have little kids or anything like that, you can bet them. Or if you have adults that think they're super strong, you can try this on them and see if they can do it. Right, so here I have my 2 textbooks, quote unquote, and here's just a regular plain old piece of paper. I'm gonna put it down there like that, and I'm gonna blow down below right here and see what happens. Obviously you can see face mask works pretty well, right? So wear your face mask when you go out. But if you take it off, then you can do this. So I wasn't blowing on the paper, I was blowing underneath the paper. So I was blowing underneath it, but if I blow on top, same thing happens. Underneath, same thing happens. So these are a couple of experiments to play around with to help us understand that air is actually something, right? And so the air that is actually something exerts forces on other things that are around us. And those forces really dictate a lot of the stuff that goes on. I mean, the reason gas mileage in some like the clunky trucks and things like that are so poor compared to like a small like Camry or something is they're bigger, they're boxier, they have more air resistance to them, right? And that air resistance means it takes more energy to drive them through the air. So how in the heck did this work? Well, oops, let me see here. Gosh darn it. There we go. I'm going to put my air molecules back underneath here, the paper. So I'm going to fill up underneath the paper, and then there's air molecules. Oh, why isn't that's interesting? It's kind of make it invisible. It's hard to see on top, but there should be, let me go like this. There should be, what the heck? There we go. There we go. There should be molecules on the top of the paper as well, all around it, right? And so on the before, if we want to label the befores here, and maybe I'll make this a little bit of a different color that's easier to see. We have, right, air molecules are acting in all directions. They're pushing up, they're pushing down. You have stuff underneath the paper pushing up, you have stuff underneath the paper bouncing down, and they're constantly kind of bouncing around, moving up and down, going all over the place here. And so that's why the paper is able to stay just kind of in its normal spot like this, is the forces are balanced everywhere. So those forces are all balanced, the paper stays flat. Now, when we blew, right, what we ended up seeing was that paper go down. And the reason that paper went down, and I'll show you why here, is, oops, doggone it. So here's my paper, kind of like this, kind of went down like this. Oh man, that one, there we go. I had the fine tip on that. That was a problem. All right, so here's my paper. You can see it bowed down and dipped down. But the reason for that, if we go back to our air molecules that are down here, what happened was most of the stuff that was underneath there got blown out. So literally the air molecules that were underneath got blown out, and it gave more air molecules more weight, basically, and more pressure sitting on top. So we kind of had this, whoops, let me go back to my other color here. We had, instead of, some of these other arrows pushing back, or air molecules underneath the paper pushing back, there is a net force of all these air molecules pushing down, because when we blew on it, let's see here, there we go. When we blew on it like this, we blew a whole bunch of those air molecules out the other side. let me see if I can illustrate this. I'm trying to think of a better way to illustrate that. Let's see. I think I have an idea. Whoop. There we go. So I'll kind of, oops, wrong way, like that. That's what I want to show, is that those air molecules are going this direction. So when we blew underneath that paper, we blew all those air molecules out, and it allowed the air molecules on top to weigh the paper down, and it caused it to bend. So this is like proof positive that the atmosphere is made of stuff, and it weighs, it has a weight to it, it has a mass to it, and it can push things down and cause it to act like this. And I can tell you 100% that it is, if you have a completely flat piece of paper and you have the two books like you see in the video here, it is completely impossible to blow that piece of paper off in one blow. It is just impossible if you have it like spaced like this. So that's why I call it the $1 million challenge, because it's really impossible. And there's another fun trick too that we're not going to try, but you guys can do it if you want. And just take one of your empty 2-liter bottles from your Thanksgiving parties, or, you know, it can be like just an empty water bottle works too, but something with a narrow neck. It can be glass. It doesn't have to be plastic, but plastic probably better. And then you just take a little piece of paper and make a little ball out of it. And if you do that, and you stick that ball in the neck of this laying down bottle, you challenge a person, okay, hey, blow the ball into the bottle and just see what happens. All right, it's a pretty fun, interesting thing, has an interesting result, and I won't tell you how it ends. You guys can play with that one on your own. All right, in just a few minutes here, or not in a few minutes, but on your own. Okay, so just to kind of reiterate, so that's our proof in the pudding here that air exists, that we can see these experiments, that air is causing things to move, and pressure differences in air causes forces to be unbalanced and causes things to move. That's going to be a big deal, especially next week when we come back, or 2 weeks from now when we come back, to see and figure out how winds are created. It has to do with pressure differences. But just to kind of reiterate, here's that major components of dry air: the nitrogen, the oxygen. Carbon dioxide is that small little slice. Argon is about 1% of it. And then there's a few other things in there too, but pretty much it's just oxygen and nitrogen. And so that's kind of one of the common misconceptions folks have, is that when you take a breath of air, that most of it is oxygen. And the fact of the matter is it's mostly nitrogen. All righty. Now, that was dry air. And on average, though, water vapor actually makes up about 4% of the Earth's air as well by volume. But it varies from place to place. So in this case, where you see orange, that represents dry air. The blues and the teals represent lots of extra water vapor that's in there. So the orange represents dry, the blues represent the kind of the moist and the really moist airs. And those really represent where clouds are, or where precipitation is, and rain and things like that. That water vapor is a big deal, because not only does it form clouds and precipitation, which is beneficial for life, right? But the clouds that form, depending on where they move, the clouds actually absorb energy or they reflect some of the energy coming in from the sun, right? Straight and bounce it off, but they also absorb heat energy or infrared radiation escaping from the surface of the Earth. So you can kind of think of clouds as like Earth's blankie, right? Or at nighttime when you get cold, you kind of pull over a blanket and it traps in the infrared radiation, the heat trying to leave your body. Clouds are very good at absorbing some of that outgoing radiation, as is carbon dioxide. So you can think of clouds as kind of like I don't know, the polyester fill for a comforter or something like that, and think of carbon dioxide and methane as like down, something like that. That's even better at trapping heat than some of those other things. So that's an analogy I just came up with. I'm gonna think about that and use that a little bit later on. So there's also other things in the atmosphere like aerosols. And so aerosols are the things that are basically tiny solid and liquid particles. So not water liquid, but like liquid of other chemicals of some sort or another. There could be pollen, it could be dust, it can be other things like that as well. But basically, those are important because it allows water vapor a place to condense and glob onto to make clouds. In a perfectly pure air with no dust and pollutants, it would be pretty hard, a lot harder for water vapor or water gas to condense and cling on to anything and make water droplets if we didn't have that. But what's kind of also awesome about these aerosols is they reflect sunlight sometimes, which is good in some cases and has a lot of negative effects in other cases. And these particulates also help color the sunrise and the sunsets. So if we take a look at this kind of, is this live? Let me see. I don't remember. Yep, this is right now. So these are where all the particulate matters are pretty high right now. And usually where you're seeing these kind of big influxes up here is either like coal plants, or this might be, I don't think they're having fires up there. So I don't know what's causing all of the particulate matter up here at this moment. But for us down here, the particulate matter that we're seeing is a result of probably car pollution. So you can see LA and the southern part of the Central Valley, it's like exhaust pipe pollutants and things like that. This is probably fires down in the Amazon. Africa, this is probably dust blowing across the deserts and things like that. So that's kind of a live view, but it'll look at some of all the particulate matters there, which is pretty interesting. And we also have, what is that? I don't even know. Purple air. That's what I was trying to find. Music video. So these purple airs are little laser sensors that people have on their houses or businesses have, and they measure the size of the air pollutants that are in the atmosphere. So you can see it says PM 2.5, particulate matter 2.5 microns across. So this is about, so the microns in that size would be about 10 times smaller than a human hair, somewhere in that neighborhood, I think, or no, about 20 or 30 times smaller than a human hair, if I'm doing my mental math right. And these are just kind of floating around in the atmosphere. And what's bad about them is they can get right into your lungs, go through the membrane in your lungs and get into your bloodstream, and then also cross the blood, that membrane in your brain that it can go through as well. So particulate matters of these sizes, if it's too high, that's not great. That's not good. And it's a pollutant that we are exposed to quite frequently in the valley. But last night we had that nice little storm that kind of blew through and helped mix the air a little bit. And we didn't get any rain, obviously, but it caused the winds to mix and got rid of the fog and kind of blew some of it to the south, like Bakersfield and Fresno and places like this. It blew all of our pollution down into the southern part of the valley, and they're now suffering much higher rates of air pollution down there. So where it's green, that's good. My guess is where it's like the really purple up here, people are probably burning fireplaces or something like that. But you can go to this website and get a real-time update of all of the pollutants that are in the atmosphere at any given time based on those little laser scanners that we have hanging on our house. We're all probably familiar with, right, the aerosols from smoke and things like that, from wildfires. And that's kind of a big one. Sorry, my eyeball itched. This is from the Paradise Fire. Was it 2018? Or Camp Fire in Paradise in 2018 here. And you can see how it just poured smoke into the Central Valley. And I mean, that was a terrible fire. It's the most destructive fire we've ever had in California. It's cost the most lives of any fire we had in California. But in terms of size, it was not a relatively huge fire. And in the last 2 years since this, or 3 years since this, we've had many bigger fires. And that's why we've had so much pollution that we've had to kind of live with here in the Central Valley over the last 10 years, or I mean, the last 2 or 3 years. And honestly, growing up in the Central Valley, there's just a lot more pollution because of the effects of the valley here. The mountains on either side of it kind of trap the air in there and trap those particulate matters. So we'll get into that a little bit later on. But if we want to look at the structure of the atmosphere here, we were looking at the books and the balls, kind of imagining these molecules exerting amounts of pressure and amount of forces on things. And another way of visualizing that is if you were standing at the surface of the earth at sea level, and you had, I just want you to imagine like a big PVC pipe from the garden, like a big white pipe that you might see that sprinklers run through. The PVC pipes are about, let's see, well, here's a tripod. Oh no, let's see, that's not about right. I'm trying to think. I don't have anything sitting around me. Or I guess, yeah, this would be about a square inch. So my pen holder here on the backside, if you imagine this was a pipe that went from sea level all the way up to the atmosphere, to the edge of the atmosphere, to outer space, and you were to trap all the air bubbles in that massively long pipe that's about 60 miles tall that goes all the way to outer space, this is kind of what it would look like. If you put a lid on it, you put a cap on it. Down towards the bottom, because of Earth's gravity, you have most of the air molecules hanging out around the surface where there's like, gravity is kind of keeping it down. And then the higher up you go, you get less and less molecules going up the higher up you go because of the air expanding, like temperatures cooling. Oh, there's all sorts of variations that cause the amount of molecules, the number of molecules to go down as you go up. But for the most part, it has to do with gravity. But the thing is, if you were to measure all of the air in there and measure the weight of that air, it would weigh about 14.7 pounds. So in that square inch of tube, if you were to go up all that 60 miles or so, at the bottom of this tube, if I were to put a scale at the bottom of my hand and weigh all the air in there, it would weigh 14.7 pounds down at sea level. And that's what we measure. That's what we mean when we're talking about air pressure. It's basically how much does the air weigh on top of you? And that's based on how many air molecules are around you. So what we're going to see here in just a minute, which is pretty amazing. Oh, hey, I know what I can do. I can draw this little picture. Where'd it go? There we go. Here's 1 square inch. So this, let's see here. That's 1 square inch. Here's my finger for scale. Okay. So if you were to put that flat, it's my reminder to record. So if you put that flat like this, basically at sea level, right there, anywhere on that square, there's 14.5 pounds of air squishing down on there. But it's not just down, it's from all the different sides. And that's why my paper is not crumpling up right now. But if I blow, well, it's hard to do because it's stuck to my hands, but if it was bigger, if I blew underneath it, right, it's going to cause a lower air pressure and it's going to cause that paper to dip down. So that's what's kind of cool. And that's what's kind of interesting about this air pressure is it exerts itself equally in all directions. But if I go up higher, so like here's sea level, if I were to go up high, like in Denver or to the top of the Sierras or something like that, the higher up you go, you get into this thinner atmosphere. And so if I'm standing right here and like, let's say it's Denver or the Sierras or something like that, I only have this many molecules weighing down on top of me. So the air pressure is less. And not only is the air pressure less, but there's fewer molecules because the air pressure, or I should say there's fewer molecules, which makes the air pressure less. But this is what makes it hard to breathe when you go up in these high elevation places sometimes and you're not used to it. Like there's just not as many oxygen molecules up there because there's not as many air molecules the higher up you go. So about half of all the atmosphere is below 3.5 miles of elevation up there. All right. And what's kind of nuts is about 90% of the atmosphere is below 10 miles. So here's about where the 90% of the atmosphere lies is here and below. And believe it or not, this is about the same elevation that airplanes fly around, is right around 10 miles above sea level, somewhere in that neighborhood. So next time you go flying in an airplane, just think about, wow, you know, I'm flying on top of 90% of the Earth's atmosphere in terms of atmosphere molecules. It still goes up another 50 miles before you hit outer space, but it just thins out and gets really, really, really thin before it's technically outer space up there. All right. So folks that climb Mount Everest, look at that. Folks that climb Mount Everest, woo-wee, there is not much oxygen up there. The air pressure is only what, like 200, no, 300, there's 314 millibars, somewhere in that neighborhood. So compared to at sea level, it's 1,000 millibars. So it's a third of what we have down at sea level. And that's why you see folks up there climbing, most of them climbing with oxygen masks and oxygen tanks and things like that, because there's just no air up there. And so there's my potato chips too. If you pack your potato chips down here at a pressure that's like, 900 millibars, and then you take your potato chips up the mountain a little bit to where the pressure is lower, then that higher pressure trapped in the bag is going to be able to exert more pressure than the air pressure on the outside pushing down on it. And it causes it to inflate, which is kind of cool. All right, so we're going to get through the layers of the atmosphere here really quick. Then we'll take a quick little break, and then we'll be able to get into, after we take a quick little break, your first couple of breakouts and do some interesting things and not just listen to me talk. All righty. So there's a couple of different layers to the atmosphere that I think you need to know, the vertical structure of the atmosphere. And they are the troposphere, the stratosphere, the mesosphere, and then the thermosphere right up here. And I'll show you some of the really important parts about them in a minute. But the main thing I just want you to see is that we basically classify the different layers of the atmosphere based on their temperatures. So if you notice, if you take a look at the temperature scale down here, the top part's centigrade, the bottom part is Fahrenheit down here. The higher up I go in elevation, the colder it gets in the troposphere. And it turns out that the troposphere is basically where all the weather in the world happens, right? All the weather, all the clouds, pretty much this is where it happens. It gets too cold, it squeezes out all the water vapor above that, and it's really hard for clouds to exist at such high elevations. It's every once in a while it's possible, but not really. So the troposphere, you can see temperatures go down the higher up in elevation you get. So it gets colder the higher up you go. And then something weird happens. In the stratosphere, look at that, the temperature line, the red line, it goes from like minus 50 or minus 55 degrees all the way back up to like 10 degrees Celsius over here, which would be in the mid 40s. And that's because the stratosphere has the ozone layer. And it turns out the ozone layer absorbs a lot of UV radiation from the sun. And that absorbing all that radiation translates into heat energy. And that's why the stratosphere gets warm. So everywhere where the heat keeps increasing in the stratosphere, that's what we call the stratosphere. And then when it stops heating anymore, we kind of call this that stratopause, and the place where the troposphere changes into the stratosphere is called the tropopause. That's the changing line names, I guess you would call it. Once you see that, you get into the mesosphere. So it starts cooling off again. The temperature starts cooling off again. It's kind of where meteors burn up. And then the thermosphere way up high, notice it's called the thermosphere. Thermos means heat. It gets hotter again because it's absorbing like radiation in terms of the solar wind from the sun to make the auroras and things like that. But even though it's pretty hot up here, it's like almost the same temperature as what it would be down on the surface of the Earth. There's so few air molecules up here. There wouldn't be enough air molecules bouncing onto your skin to actually make you feel hot and make you feel warm. It just means the molecules that are up there are moving pretty fast because they have a lot of energy to them. But it really wouldn't make you feel warm at all because there's just not enough molecules imparting that energy to you. All right. So that troposphere, it gets colder. We'll talk about these temperature decreases a little bit more later on in like next week or 2 weeks from now, I guess. But the higher up you go, for every 1,000 feet you go up, it cools off about 3.5 degrees or 3 degrees Fahrenheit for every 1,000 feet you go up, which is why in the summertime, when you go up to the mountains, it's much cooler up in the Sierras than like up and down in the valley here because you're going higher. And that has to do, we'll learn next week about air expanding and the pressure dropping. And as the pressure drops and the air expands, it causes a cooling effect. It's called adiabatic cooling. All righty. So we already talked about the stratosphere and how it absorbs, the ozone layer absorbs all that UV radiation. There's our mesosphere and all that good stuff. And a couple of other things I just want to make mention right now is the ozone layer is made up of 3 molecules of oxygen, or 3 atoms of oxygen. That's what makes an ozone molecule there. All righty. Its distribution around the Earth is not uniform. It's about 10 to 50 meters up high, but the good thing about it is it absorbs that UV radiation, like I was telling you about. That's important for life. If we had too much UV radiation, it would, cause mutations and cancers, and things wouldn't be able to live. They just get fried. That's why you can take a UV light and treat your water with ultraviolet lights in some places where you have contaminated water. and it'll kill the germs and the bacteria because UV light is very powerful. So if we didn't have the ozone layer, it would be bad. And so back in the early 70s and 80s, we started, or 70s, it was starting to be recognized that hairspray propellants and air conditioning fluids and things like that, when we sprayed them and they got into the atmosphere, they created what we call chlorofluorocarbons, or the chemicals that were making these propellants were called chlorofluorocarbons. And once they got up into the atmosphere, they would actually attack the ozones and break them apart and turn them into just regular old oxygen molecules. And when that happened, it ended up creating a huge hole in the ozone. And in one of the first instances of the whole entire world agreeing to do something good for the good of humanity and the good for our future existence, with the Montreal Protocol, I think in the early 80s or late 70s, I can't remember the exact date, they basically banned all of these chlorofluorocarbons and other materials that would deplete the ozone layer, because there's a recognition that says if we don't fix this, hole's gonna keep getting worse and worse and worse, and we're gonna see it's gonna make it harder for people to live and things to live on Earth. So humans can get together and do great things and fix the things. And so we've stopped emitting a lot of these, but it's going to take another 30 years or so for some of those CFCs to finally fall out of the atmosphere. And so for the time being, the hole in the ozone is actually shrinking a little bit, compared to what it was like in the late 80s and early 90s. But it's kind of fluctuating. And so we need to double down our efforts to make sure that it stays, so the ozone doesn't keep getting depleted. And I just also want to mention about the ozone layer. Ozone layer has nothing to do with climate change, all right? Climate change, ozone, completely different things. Ozone blocks ultraviolet radiation. Climate change, you'll see, is a result of carbon dioxide and methane molecules absorbing infrared radiation. So with that being said, it's 5:39. We went a little over here for the first part. So let's take a quick 5-minute break. All right, we're going to take a quick 5-minute break. So what time is it? 5:39. Let's come back at like 5:44 then. Go get a snack, go get a drink, whatever you need to do. When we come back, I'm going to show you this cool little model that you guys get to play around with for a little bit. And then we'll go from there. All righty. So see you in about 5 minutes. All righty, welcome back. Take a quick deep breath here. Maybe by the end of Thanksgiving break, I'll have a fun little project I've been working on to be able to share with you guys. It's really dorky, but I think some of you might enjoy it. You'll see, it'll be pretty cool. All righty, so here's what we're going to be doing next. All righty, we are going to be using this really cool, we call it's the Earth Sun app. Professor from, I don't remember where Dr. Marsh is from, somewhere in the world, used his amazing talents to put together this really awesome kind of Earth Sun relationship viewer. And oh, that's, I forgot to mention last night, there was a 98% lunar eclipse, a very long lunar eclipse, one of the longest lunar eclipses that it's going to be around for the next couple hundred years. But we had clouds, and so most folks around here were not able to see it last night. But if you Google like lunar eclipses from last night or something like that, it'll pop up for you. So what we're going to do is we are going to try to take a look and try to start making some sense of what is going to be the thing that's going to heat up the atmosphere. What's going to be kind of the driving force that creates the atmosphere's energy, right? Where does it come from? And we know it comes from the sun. So hopefully with this, I'm going to give you guys a chance to play around with it here in a few minutes. You guys are going to be answering a few questions. And so let me get out the Jamboards here. Copy link. It's Friday. Yep. Okay. Let me just make sure I have the right ones here. So here's the Jamboard. I can spell. What the heck? Oh, I guess I didn't copy it. Give me a quick second here. There we go. Copy link. There we go. Jamboard. So on that Jamboard, we're going to be getting into small groups here, small groups for sure. You're going to open up that simulator app. So in the background, this is just a picture to show you what the actual app looks like. But this is the background of it. The actual app lives right here. So I'm going to copy this. I'm going to paste that. The app is right here. So when you click on that, it's going to open this. So you can click on it and open it right now if you want, but I'm going to show you a few things to help us understand how this works, because what you're going to be trying to do here is you're just going to play around with this app for a few minutes. And basically, you're just going to write down some notices and wonders. So no notice is too big, no notice is too small, just some things that you notice and wonder, just goofing around with it. All right. So after completing these first two things, I want you to move the geographic location point to an area near where we live, all right? And then to a different place on Earth and play around with the time. So for example, what do I mean? Well, so we have this funny thing right here, right? This is kind of showing us and pinpointing where everything is. In this case was in England, I think, or where this person lives. And oh, a couple of shortcuts here. If I click my mouse button down, or not my mouse button, but the mouse wheel, like the scrolling wheel, if I hold down on it, that allows me to drag the Earth back and forth like this. If I just left click on it, it allows me to spin it and orbit it around. So either left or right click allows you to do that. If you're using a touchpad, I don't know, because I haven't used it with a touchpad before or a laptop, but you can goof around with it. All right. So just click around. What do you notice? What do you wonder? There's lots of cool things to click on down here at the bottom, like sunbeam. Oh no, by the way, you can zoom in and zoom out like this too, right? And you can see different things. Oh, hey, there's the sun way out there. Depends on what you want to do. So there's the sunbeam. You can click on some of these other things to figure out what that might look like and what it means. All right, just to goof around with it. What do you notice? What do you wonder? That's some pretty good stuff. I'm going to leave that on there right there. So after you play around with it, then what you need to do is when it says move it to like one of our locations, the way you do that is you click this little globe part in the top right-hand corner, and then you can click your location, and hey, look at that. It'll find exactly where we are. All right, so that'll do your location. Or if you want to change something else, you just move the slider up and down like this. And if you want to change longitude, you can go like this and move it around the Earth. All right, so once you find a place that's pretty much us or you, or choose something else, then On the right-hand side, you'll notice there's this timer here. This is pretty cool. This timer basically goes throughout the year, and you can go through like this, or if you go in the top left-hand corner, you can press the play button. And I'm going to, you can speed up the speed like this and make it be like a disco ball where the daylights are like this, or you can make it speed up like this, and you can see how the sun angles change over time. Here's February, right? If you want to make sure, if you want to go down to different times of the year, you can do it like that. It's up to you. Now, there's this part to play around and function with and tinker around with and see what the heck's going on. And then what I want you to try to do, though, is think about what time of year has the most direct sunlight for any spot on the earth that you guys are looking at. So what I mean is, if I can find the right one, is I'm going to stop this. Bloop. All right. The blue lights here. Oh, and by the way, if you want to change the time, you can click the clock right here, and the clock will do the daylight hours. And then if you unclick the clock right down over here, it'll make it, oh, what the heck? Go back, oh, calendar, click the calendar, and the calendar will make you go the time of day like this, okay? Make you go up and around and down. So when I say the most direct sunlight, what I mean is, when is this blue line coming from the sun as close to coming straight down as possible, right? For these different locations. So if I'm standing in Turlock here, here's July. We know July is kind of the summertime, but look at that. The blue line is pretty as close to straight up and down as it's going to get, depending on the different times of year. So that's what I just want you to goof around and play around with. All right, it's taking a look at that. And then also, if you want, you can click the heliocentric view a little bit later on and play around with that and see what happens when you goof around with that. So I'm going to give you about 10 minutes here with this one. It's not like super duper, I just want to give you a chance to play around with it and see what you think. So what time of year do you think is going to be the warmest? When do you think it's going to be coolest? And play around with that, get some notice and wonders down. And then once we do that, I'll give you a few other pieces of information and we'll go on to the next step here. All righty. Shucks, let me see. Breakouts. Trying to find it. There we go. We'll just do 4 breakout rooms. That way, there'll be a few groups of 4, a few groups of 3. You guys can share your screens, do whatever you want to. Each person can play with it on their own, and then add to the Jamboard. You can talk about it, and all that kind of good stuff. And we'll go from there. All right. So we'll make this one. Let's say like let's go 8 minutes here. All right, 8 minutes. Explore, see what you come up with. Get as many notices and wonders down as you can, and see what we see. All right, so welcome back. Sorry, I was finished. I was reading the last little bits of your notices and wonders. So I know 8 minutes is not nearly enough, but we had so many good questions at the beginning of class. We got to get moving on a little bit here, and so I can show you a few things too. And you can always go back and play around with this on your own. It's just there's so many things to click around and play on, and you can never break it. That's the great thing about computer models, right? You can never really break it. But yeah, hopefully we saw that, right around, June, right around that neck of the woods, that's kind of when the blue arrow was most above us when we're talking about noontime hours. So if we set it to 12 o'clock or somewhere in that neighborhood, that's kind of when the arrow was highest up. And that's a big deal because we'll see in just a minute here, the more direct the sunlight angle is to us, or the more directly overhead it is, the more energy the surface of the earth actually absorbs. And the more energy that it absorbs, if it hits the ocean, it's going to warm the oceans up in those areas. And if it hits the land in those areas, it's going to heat up the land, which then is going to heat up the air on top of it. So the sunlight comes through, it heats the land absorbs, I should say the land absorbs the radiation, and then the land gets hot, and then it radiates the heat upwards into the atmosphere. That's generally how it works. So what are you guys had all great notices and wonders. You all came up with pretty much about the same thing. So a couple of things I just want to show you here is if I go back to this heliocentric view of the model, and let me close the breakouts and a few of the other things so I can navigate here without clicking through all the Zoom things. So check this out, right? If I press play right here like this, and I'm going to make that spin around and around and around, this is how the Earth orbits the sun, right? So it revolves around the sun. It rotates around its axis. So we call this motion around the axis rotation. We call the orbiting motion revolving or going in a revolution around this. So what's kind of interesting and pretty cool here is that you'll see that no matter where it is, and I'll stop it here so you don't get seasick spinning it around. No matter where it is, the Earth's axis is always pointing in the same direction, right? It always has this kind of same lean to it. So over here, it's still leaning to the left of my monitor screen. If I go to like March, it's still pointing to the left of my monitor screen. If I go over here to summertime, it's still pointing to the left of my monitor screen. Now, this has a big effect on what the sunlight does, right? This is basically what causes the seasons around the Earth, or not basically, it is what causes the seasons around Earth. It has to do with the sunlight tilt. And let me get back to noon or so our time right here. Okay. So what you can see here, if I zoom in and let me turn on the sunbeam, there's the sun and there's the sunbeam hitting the Earth here. In the summertime, the North Pole axis is pointed towards the sun. And as it points towards the sun, it allows places in the Northern Hemisphere to basically tilt towards the sun and have more direct light. Now, if I go all the way around to the winter time, check out what happens here. If I go to like December, January, now the axis is still pointing the same way, but take a look at this. The angle of the sunlight at noon is much lower. And so we don't get nearly the amount of direct sunlight, nor do we get as much daylight hours during the day, right? The days are much shorter in the wintertime. And this is what causes the differences in heat. The one thing that is pretty, I hope is maybe a little bit obvious here, is no matter where we go around the Earth, the sun is always going to be between these two lines in terms, or not, the sun's not going to be between these two lines, but these are the tropics here. So like the Tropic of Cancer and the Tropic of Capricorn down in here. And what's pretty awesome about this is in the summertime, the sun is directly overhead where this yellow line is. And in the wintertime, the sun is directly overhead where this yellow line is. And anywhere in between, the sun is always going to be at some point directly overhead in these areas. If you're outside of these lines, the sun never comes directly on top of you. Oh, Valeria, go ahead. Question.
When we were in our groups, I was trying to tell my group about how I don't have the word, but I know there's a word.
Okay.
About when the sun is directly, like, I know it's something with like it's at the peak of its time, like it's the hottest it will be throughout the day. Do you know what that word is?
Like the zenith? The zenith is that the word? So yeah, the zenith is kind of like the peak, the highest point of the sun during the day.
Yeah,
that's the word. That's the word. All right. Yeah. So and notice I'm keeping it at 12 o'clock for this. So yeah, that's a good word. And there's a lot of astronomy words that mean a lot of things, but I think zenith is the one we're looking for there off the top of my head based on your descriptions here. But what's the other cool thing is if I put the Arctic and the Antarctic circles on here as well, and I kind of zoom back in over to here, you'll notice in January, I'm going to click on the time of the days. As I spin around, it doesn't matter what time of day it is, the sunlight never really gets above this line. So it's basically anything above this line is 24 hours of darkness once it crosses, these certain points of time. So 24 hours of darkness until it gets all the way back over to springtime, the equinox over on the other side here, which is pretty nuts. Now, on the opposite end of things is 24 hours of light for the most part around the circles down over here in the summertime. So when we're tilted like this, that's our winter time, but it's the southern hemisphere's summertime because it's pointed directly at the sun and it allows more direct energy to be absorbed by these areas. So this is one of the major temperature controls and climate controls of the Earth, is how we're pointed. All right. And we're going to see in 2 or 3 weeks from now too, that our Earth, as it rotates and goes around the sun, it has a little, what we call precession and wobble. So the top kind of does this. So if you ever spun a top and see it spinning, and then towards the end, it starts kind of wobbling around before it falls over, our axis kind of does the same thing. It wobbles back and forth by about 1/2 degree every 10 or 11,000 years, somewhere in that neighborhood. And then there's changes in its orbit and a few other things that we'll talk about. And that can cause, basically the changes in angle can cause ice ages and stuff like that, which have happened throughout Earth's history, which is kind of cool. And that's kind of what causes this. But we're going to see that those happen so slowly and not on human time scales that it doesn't account for the stuff that's causing climate change to happen with the carbon dioxide and things. So I just want to say another misconception that some folks have is that, oh, we think in the summertime it's hottest because we're closest to the sun, right? And so if you look at Earth's orbit right here, it's elliptical, but it really looks, I mean, it's elliptical, but it's an ellipse that's pretty close to almost being a circle. It's not quite a circle, but it's elliptical nonetheless. But I just want to show you is right around here, the perihelion or perihelion, which is January. Oh, what time is it? Trying to think of the date time here. What do we got? Yeah, right at the 1st of January, somewhere in that neighborhood, generally speaking. This is when we're actually closest to the sun. We're 147 million kilometers away, or about 91.5 million miles, I think, somewhere in that neighborhood, if I do the math in my head. And it turns out, right, so that's we're actually closest to the sun during our winter time. And during our summertime over here, we're actually another 5 or 6 million kilometers away from the sun during our summertime, because it's not a circular orbit, it's an elliptical orbit over there. So that's another misconception. I just want to make sure we all have in our brains that seasons are not caused by closeness to the sun. The seasons are caused based on the Earth's tilt. So what do you call it? The fall equinox. This is where basically everywhere on Earth, no matter where you're at, from the North Pole to the South Pole, gets about 24 hours or 12 hours of daylight and 12 hours of darkness, pretty much everywhere on Earth here. And same thing over on the spring equinox. That's when it transitions over from the South Pole getting all the light to then the North Pole getting all the light. And, there's folks that live above the Arctic Circle. There's what used to be called Barrow, Alaska, which I don't know how to pronounce the native name for the city. Udavik, I think, is the closest one that I can think of. I need to look it up and how to pronounce it. But they just went yesterday. They had 53 minutes of daylight yesterday, and now they won't see the sunrise again until like the end of February or something like that. So I don't know. I don't know if I'd be able to live with that much darkness. But the trade-off is in the summertime, right? You basically have the sun not setting almost all summer round. But here's the thing. Up in those areas, even though you have so much sunlight, let me go back to just the Earth one right here. Oops, doggone it. Let me just go back to the Earth. Even though you have so much sunlight higher up in these higher latitudes, oops, sorry, let me go up here like this. So this is representing, this would be like April. So let me go to the middle of the summer like this. You'll notice like there's a lot of sunlight. And if I spin the globe doesn't matter where they are, they hardly have very much of a dark period at all, right? Maybe 2 or 3 hours of darkness in this area. And I think Barrow is like right over here, or what used to be called Barrow. The thing to notice is that the sunlight coming in is at such a low angle, it doesn't absorb very well into the earth. It's taking that energy and spreading it out over a much bigger area. So even though they get 24 hours of sunlight in some of these cases for a few months of the year up there, the angle of the sunlight is so low, it doesn't really produce a whole heck of a lot of warming energy up there. All right, so that's another thing to just kind of keep in mind as we move forward with the next bit. So what is that next bit? This is it. A couple of other things, just to kind of put it into goofy graphics, that if my other explanations weren't very good. So remember, the Earth's motions, it rotates on its axis, it revolves around the sun. So this is rotation, this is revolution here. It takes about 365.25 rotations to go around the sun once, to do one revolution. That's our year, right? And one day would be one rotation. That's why we have a leap year, right? Because it's not exactly 365 rotations, it's 365 and a quarter. So every 4 years, that adds up to one day. And that's why we put the leap day in February to kind of keep us on track here, right? So the seasons basically are caused by the changing of the angle of the Earth's, or the relative angle, I should say, of the Earth's axis to the sun. So the axis is always pointing the same way, no matter which way you're going. In this case, it's to the right of my screen now. It doesn't matter where, it's always pointing that same direction. But because it's at that tilt, it causes the sun to hit different parts of the Earth at different times in the year. Okay, so check this out. If you were to go outside and kind of measure the sun and look outside and look up every single day when you go outside, this is what you would notice. We're about 37 degrees north latitude, so it would be very similar to what this person is seeing. 40 degrees north would be more like Chico or something like that. Oops, somebody has a question. Okay, yeah, no problem. Thank you. Bye. Somebody has another meeting they have to go to. But what's pretty cool about this here is this is what it would look like if you went outside in the height of the summertime, right? The longest day of the year, the sun is going to be about its highest point above your head. At spring and fall equinoxes, so like March 21st, September 22nd, the angle of the sun is going to be about 50 degrees up from the ground, so not nearly as high. And then in the wintertime, look at this, the sun angle is only about 26 degrees. So next month when we have Christmas time, right around that time of the year, the sun barely gets above 25 or 26 degrees above the surface of the ground where we live here. And if you're interested in engineering or anything like that, you want homes that are heater friendly, you can design windows and window shades that basically block out the high summer sun, but let in the low angled winter sun, and you can let the low sun come in and heat up your house, just from the sunlight going in, like a cat laying in the sunbeams or something like that. That's what you can do there. Alrighty, so that's just kind of a peek of what would it look like if you were a person standing on the ground there. So a couple of other things, and this is what I was mentioning earlier in terms of the sunlight not being as direct in the northern and southern latitudes here. At high noon, so this is basically high noon in all these different places, but at the equator, the sunlight would be coming straight down, all right? At a latitude of like, 45 degrees or something like that, you get a much more angled sunlight here. And at the poles, you get even more angled sunlight. And the good analogy here is like taking a flashlight. If you've shown a flashlight straight down onto paper, all that brightness is going to be directed in one small area if you're just holding it straight down. But if you tilted it off to the side, it's going to spread that light out over a much larger surface area. And as it does that, it's basically spreading out that energy over a greater area. So there's less energy per unit area. And that's what happens up in this direction over here. Right. So solstices are basically the longest and shortest days of the year, depending on where you're at. So for us, the summer solstice is June 21st. That would be the winter solstice for the folks down there in South America and the south of the equator, I should say. And then the winter solstice for us would be December 21st, December 22nd. So we only have another month or so until we finally start gathering more hours in the day. So the day lengths are going to keep getting shorter until these 2 days right here. And then it's going to start getting longer and longer and longer, which is yay for us, right? And we have these really amazing satellites now orbiting the Earth, these geostationary satellites, to help us see the weather changing as the day goes on. These satellites are up 220,000 miles above our head, believe it or not. And they orbit the Earth. They fall around the Earth. They orbit the Earth at the same rate that the Earth rotates around its axis. So what that relatively does is it makes it look like no matter how the Earth turns, the satellite stays in the exact same spot, and we get some really amazing views. And what you can see, right? You can totally see the angle of the shadows of the Earth. This is definitely a wintry time type setup for us, because you can see the shadow goes through Canada and things like that, and everything's dark up there. In the summertime, this would be lighter, and that the shadow would actually go this away instead of that away. So a couple of other things. I'm going to go really quick with this. All right. So hopefully we can get into our last little exploration here. So what comes out of that sun? We looked at the sun, we looked at the sunlight, but what comes out of it is electromagnetic radiation. And one of the most abundant types of the electromagnetic radiation that comes out of our sun is visible light. And so remember, visible light is made up of all these different wavelengths of light, like anywhere, the colors of the rainbow, right? From violet all the way to red. The Roy G. Biv, remember red, orange, yellow, green, blue, indigo, violet. If you want a song, you can click on it, and there's a cool Roy G. Biv song. But there is also sometimes, or not sometimes, but it does emit low amounts of gamma rays and X-rays and things like that. Sometimes radio waves, microwaves. But the most that comes out of our star is in this wavelength. Other stars in the solar system, other stars in our galaxy, not our solar. There's only one star in our solar system. That's the sun. But other stars throughout the rest of the galaxy here, they, if they're bigger and burn hotter, they emit way more energy, way more total energy, and they emit more of like the gamma rays and X-rays and things like that. And older stars tend to emit more of these longer wavelength, lower energy type radiations over here. And what you're seeing in this picture, this is our sun, but it's imaged in all the different wavelengths of light that are different wavelengths of electromagnetic radiation that it spits out and sends our way. And I do want to show you one quick thing here. The difference between like gamma rays and radio waves and light waves, they're all part of the electromagnetic spectrum, which means they all travel at the speed of light, right? They all travel at the speed of light. The only difference here is that gamma rays, imagine this is a wavelength, and each one of my folds in the crumple here is a wavelength. Gamma rays, their wavelengths are, let me see here, pushed together like this. Visible light with the wavelengths would be spread out a little bit more, and then radio waves would be spread out even more. But each of these would still be traveling at the speed of light. It's just the distance between their waves is the only thing that makes one thing different from another. And if you take a physical science class or a physics class or something like that, you can get into it a little bit more than what we're getting into it in this class here. But the long story short, the takeaway that I want you to have from this is to know that our atmosphere is really good at letting visible light through. So visible light can get through our atmosphere pretty good. Some ultraviolet radiation can get through. This is why we have to wear sunscreen when we go out in the summertime sun, because there's still some ultraviolet that gets through and can cause cancer and all that other stuff. But also some infrared radiation can get through. So some like heat and things like that. But the other thing that's pretty nuts is that, and that's good for us, is radio waves are really good at going through our atmosphere. And it's really good for us because if we couldn't get radio waves through our atmosphere, we wouldn't be able to communicate with anything out in outer space. And that would be bad, right? That would not be so great to have all those things communicate and do that, or not be able to communicate with them. And also, I just want to make mention here, these lines are showing where these things get absorbed in our atmosphere. So how high up, or I guess how far down into the atmosphere they get before they get absorbed. So gamma rays and X-rays, even though our sun, it still puts out some, it's not a whole bunch. Most of those really powerful, like things that can cause damage to tissues and living organisms, they get absorbed up in the stratosphere, along with a lot of the ultraviolet stuff in the ozone layer and other parts of the stratosphere. So all these high energy stuffs, our atmosphere actually absorbs and prevents from getting down to the surface, so we can live our happy lives without worrying about getting too toasted by some of this radiation from outer space. And luckily, radio waves, they don't do anything to us. I mean, if they did, we wouldn't have Wi-Fi and any of that other stuff. I mean, there's just radio waves going around us constantly right now that we don't even notice, which is pretty awesome. So a couple of things to remember about the way heat can be transferred, and because we're going to be talking about this over the next couple of days or the next couple of classes. Radiation is basically, it's electromagnetic radiation. It's where energy, long wave infrared radiation, radiates out. It's how you can feel a hot fire. Even if you're 10 feet, 20 feet away, you can still feel the heat off the fire, even though the fire flames are not touching you. That's radiation, right? So that's basically the electromagnetic radiation coming towards you, coming through the air and smashing into your skin, which absorbs that infrared radiation and makes you warmer, right? That's one thing. Convection then usually causes these vertical motions, these mass movements within a substance, kind of usually a liquid for the most part, but we saw with plate tectonics, there's convection happening in our mostly solid Earth as well. But this causes kind of this mass movement of things. Boiling water is a great example. And then conduction is where if you were to heat up a metal rod or a metal handle, basically the moving molecules on one end that are really hot cause other molecules to start wiggling really hot as they bump into them, and can make the whole, in this case, metal handle hot. So that's what we call conduction, where the heat kind of travels up that way. What we're going to be focusing on for right now is radiation, and then a little bit later on, we're going to be talking about convection. And you know conduction if you've ever tried to walk barefoot across a blacktop during the heat of the day, right? That's not a pleasant thing to have to do. So how does the atmosphere get heated using this radiation? Well, there's a couple of things that we need to know. And the first thing is albedo. So the albedo is basically the reflectivity of a surface. So how reflective is the surface? How easy is it to reflect light that comes in? And when I say reflect, it's just like looking in a mirror, right? The light bounces off and comes straight back at you. It's not absorbed, it's just boink, reflected and goes back out. So albedo is the way the scientific way we put a number and quantify how reflective these surfaces are. And it turns out, if you see a higher number here, that means they're very reflective. So the bigger the number, the more like a mirror they are, all right? The lower the number, the more they absorb everything. So like asphalt is a really, really good absorber. Dark roofs are very, very good absorbers of the visible light that comes in from the sun. And visible light is a shorter wavelength than infrared radiation. Well, that's a big deal. We'll talk about that later on. But basically anything that's dark is going to be a better absorber, and everything that's lighter in color is going to be a better reflector, right? And that's going to cause differences in how things heat up on the surface of the earth. Things that are darker warm up faster. Things that are lighter, wider, brighter are going to reflect light that comes onto it, and it's going to prevent it from heating up as quickly. So think about like the North Pole and the South Pole and things like that, where you have lots of ice caps up there. A lot of that sunlight's going to get bounced. So to kind of make just a goofy little animation for y'all, that visible radiation, when it comes in, about half of it is absorbed by the land and the sea. About 5% of the sun's light is reflected off of the land and the sea. So maybe it hits a lake, or it hits some bright water, or it hits some snow or something like that, and just boink, reflects all the way back out. Some of it is 20% of it's absorbed by clouds. All right. 5 of it is scattered back into space. And so scattered, what that means is it takes the the wavelength of light, or like the electromagnetic radiation coming in from the sun, and it basically hits like a piece of dust or a water molecule or something like that, and it kind of splits the wavelengths of the light and causes it to go in all sorts of different directions. So scattering basically means it never gets to the surface. It just gets kind of, the light rays get weaker. And that's about 5% of the radiation that comes from the sun. And then the last 20% is literally radiation is reflected off of the clouds. So we have 5% reflected from here, 20% reflected from the clouds. That's like a quarter of all the sun's energy coming into the earth just gets reflected and doesn't get absorbed, but half of it gets absorbed, right? That's a big deal. Half of it gets absorbed, and when it gets absorbed, it starts transferring its heat to other things. And this is just another way of saying what I just did. So I'm not going to spend too much time on the sky is blue and things like that for right now, other than to say we're talking about scattering here, is when the sunlight comes in as visible light, which is all of the colors of the rainbow together make white light that we see. Air molecules, oxygen and nitrogen molecules, they happen to interact with the blue wavelengths of light coming in from the sun, and they kind of get caught up and scattered and basically thrown back out to the sky. And so when we look out, when we look up, what we're seeing is those blue wavelengths being tossed back up into the sky on a bright sunny day. That's just kind of why the sky is blue. Now, at sunset, when the sun is lower, the sunlight has to go through more gas particles and more dust particles and things like that. And as it does that, it basically smashes out and filters out all these shorter wavelengths of light. And the only thing that can pass through all of this and reach our eyes is going to be the longer wavelengths of red. And that's why we kind of see these redder sunsets here. So if you want to study this a little bit later on your own, you can, but that's how we get blue sunsets and things. And I just want to show you a quick little idea of what scattering can do. So this is a tub of water, and I have a flashlight on the other end, and I'm putting in some of these drops of milk. And I want you to see what happens to the color of the light as we keep adding more particles in there. So more milk particles in there, we swish it around. Notice that as it gets thicker and thicker and we introduce more milk particles that the light has to go through, it's going to start filtering out those blues in that coloring and only allow the longer wavelengths that don't really hit the milk. It allows the longer wavelengths to get out to the other side. And if it keeps going, the more and more particulates matter you have in the atmosphere, the redder and redder the sun or the source of the light will look, right? Which is pretty cool. And we're probably way too familiar with that these days now with fires and things like that. So this is what white light looks like. If you were coming in from the sun, I decided to make this last year to show you guys what it looks like because I was bored one day. But there's white light. It's composed of all the colors of the rainbow. And that's what's constantly bombarding the earth, right? Is this white light constantly bombarding the earth on a daily basis. Now, when that white light hits our atmosphere, I'll kill the music. Oh, go back. When it hits the atmosphere here and it hits an air molecule, those blue wavelengths of this whole entire white packet of light here get scattered first. All right. And then, that's the thing I want to show you is now there's less blues and purples, which leaves behind the reds and the yellows and the oranges. So it makes it more of a yellow light. So it goes from white to more of a yellow light. And if it hits like a smoke particle or something else, it scatters the rest of the blue and the purples and leaves only the reds and the oranges. So you'll see that now it becomes orange light. And if it hits another particle and scatters even more, it becomes red. So that's why we get these different colors. And especially if we're seeing like a forest fire in the Coast Range, the white light that comes in from the sun, the more times it hits a particle or the more pieces of smoke particles or air molecules it hits, the redder and redder it goes. It acts like a filter. All right. Man, it's so silly that like this 5 seconds of film took like an hour and a half to make. But anyways, that's what it did. And so there's our scattering of the blue. There's our sun setting like this. And then here's some of the forest fire smoke that was over us last year when the Coast Ranges were on fire over by Del Porto Canyon. So this is why the sun kind of looks like Mars, or we look like Mars on these smoky days, is all those particles of light that are white get filtered through the smoke, and only the longer wavelengths of red light make it through. Okay, so we want to focus now on that energy and that light that gets absorbed by the Earth's surface, because what happens is when the light comes through, it doesn't really, not too much of it, remember, gets absorbed by the atmosphere, absorbed by the clouds. Some of it does, but not much. Most of it gets absorbed by the surface of the Earth. And when that happens, that energy, that visible wave-like energy, when it hits the surface and absorbs in these darker materials, so remember, the darker the material, the lower the albedo, the more it's going to absorb that energy. The more energy it absorbs, the more its molecules are going to wiggle, which creates heat or infrared radiation or thermal energy. And it's going to then radiate that heat from that surface of the Earth. It's going to radiate that heat up into the air above it and transfer that energy to the surroundings. All right. So like I said, blacktops, asphalt, things like that, streets in the middle of a summer day, right? That's super duper hot because as a low albedo, it absorbs so much energy and then it radiates that energy back up to, into the atmosphere. This is what causes places to be hot or cold. It has to do with how much energy is being radiated back up into the atmosphere. Places where the atmosphere is over high albedo or low albedo areas where there's lots of radiation going up into there, it's going to absorb more heat and they're going to be hotter. And so you can do that by either being darker, or you can do that by having more overhead direct sunlight coming in to you, like near the equator or something like that, over a given period of time. So that comes in and then it radiates back out. Now, if we didn't have an atmosphere, all of that radiation would just escape back into outer space and we would freeze to death every single night when the sun goes down. Luckily, we have greenhouse gases like water, like carbon dioxide, and like methane. At these kind of normal levels, when we evolved as humans, and in the last 200 million years, we've had these varying amounts of greenhouse gases in our atmosphere. Not 2 million years, but for the last, greenhouse gases have been around since the beginning of the Earth's atmosphere. But the proportions and the amount of them have changed. My point is that they are good at trapping outgoing infrared radiation. So they, again, are kind of acting like Earth's blankie, this time not as clouds, but this time like these little molecules here. They absorb some of that outgoing radiation and they keep the atmosphere warm. And if the atmosphere stays warm, it's going to then transfer some of that heat energy back down to the ground and keep the ground warm. So it's kind of this weird thing where the ground gets energy from visible light, it radiates heat upwards, heats the atmosphere that can absorb it. And then when the sun goes away, some of that heat gets radiated back down to the Earth and keeps us nice and cozy. So I have a quick little video to play that I think explains it better than I just did. So let's see. Oops, it helps. Helps if I unmute it. There we go.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere—
So I think this is one of the things in the sketch notes that I ask you to think about and draw is right here. So look how these molecules move and how they behave, all right?
is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder.
So basically what's happened here when they say it's much, much harder is in the last 100 years, as we've been burning more fossil fuels, that's created quite a bit more carbon dioxide. And then we drill like for natural gas and things, it allows methane to come out. It's basically those molecules are staying up in the atmosphere. And because they are greenhouse gases, the more molecules of those are up in the atmosphere, the more trapping energy, the better they do at trapping energy, which keeps the Earth hotter over time. All right. So it's these wiggling, the vibrations and the wiggles of these molecules is how that heat gets trapped. So it radiates out and then it hits these greenhouse gases that cause the gas molecules to wiggle and jiggle even more because those wavelengths from the infrared radiation make them wiggle. Another way, I just had this idea, it's not exactly the same thing, but it kind of works similarly, is microwaves work by sending microwave radiation. So it's a longer wavelength than what visible light is, but those longer wavelengths work really good at exciting water molecules. And that's how we can use microwaves, is we use those microwave energy to wiggle water molecules in the things that you're trying to heat up, which is why your plates don't get hot. If there's no water in them, there's nothing to wiggle and vibrate and get warm. All right, so let's see here where we're at. Okay, we're doing all right, I think. Oops. So a couple of last little things I just want to share with you here then in terms of these greenhouse gases and radiation. The moon, all that solar radiation that reaches the surface of the moon, it gets reflected back into space. Some of it's absorbed and then radiated back out into space. But like you just saw in the little video clip, what comes in basically goes out. So it freezes at night because there's not much left there. And in the daytimes, it gets super duper hot. The Earth is pretty doggone balanced, right? Which is nice. Some of that long wave radiation eventually escapes into outer space, but not before it keeps warming the Earth a little bit. And what's nice is it's pretty balanced, right? It keeps everything, Earth's surface, generally speaking, if you were to add everything up and average it out, it keeps it out about 59 degrees Fahrenheit, which is nice. And you know, that would suck if we didn't have that, right? It would be pretty bad. And then the like really bad example of greenhouse gases are what's happening on Venus. And Venus is almost the exact same size as Earth. The only difference is it's closer to the sun. But not only is it closer to the sun, its atmosphere is made up of mostly carbon dioxide and some other sulfuric gases that are up in there that absorb radiation really, really well. And so what light comes from the sun and it actually makes it to the surface, it becomes trapped as it heats up and tries to go out. There's so much greenhouse gases in Venus that it absorbs the radiation and makes it hotter, and it keeps getting hotter and hotter and hotter because more radiation is kind of being trapped in then is being let back out into space, and it keeps it at about 900 degrees Fahrenheit, somewhere in that neighborhood, which is why we don't have rovers going around on the surface of Venus. Like pretty much everything melts after an hour or two. The Russians in the 70s put a probe on there that landed and took a few pictures from the surface, but everything else, not so much. It just melts and goes away. So that's what we're going to be taking a look at. Okay, so last little bit here, and then we'll see. We'll see where we're at and see if we do our last breakout or if we call it a night. We'll just see here. So a couple of last things. So that's the structure of the atmosphere. That's how the atmosphere gets heated, the absorption, all the stuff we just talked about. Now, those mechanics are what's responsible for the weather and the climate of an area. And let me escape this and put it back. Doggone it. There we go. That's what's responsible for the weather of it and the climate of an area. So there's a couple of terms I just want to clear up. What is weather? Well, it's like I showed you at the beginning of class, but it's the conditions kind of in the lower atmosphere over a shorter period of time. So we're talking like over a period of hours or a period of a few days. That's a short-term measurement of things like temperature, humidity, the wind speed. Humidity, by the way, is how much water vapor is in the atmosphere. How much cloud cover there is, precipitation like rain or snow, or air pressure. So how much weight of those air molecules is pushing down. And we're going to see, especially next week, as weather systems come through, the amount of pressure can go up and down depending on the types of weather systems that are flying overhead. So when you go to like websites, Weather Underground websites and things like that, and you click on it, this is the weather. All right, that's what you're looking at. All these things are the measure of weather. Now, climate, on the other hand, is if you were to take an average of all that weather for like a certain month. So like if you were to think about Turlock in January, you would take all the high temperatures from January from like, let's say 30 years worth of time, and you'd average all the high temperatures from every single day and every single one of those Januaries over 30 years. You add them all up, get an average, and see what is the average high temperature in January for that place. Or you can do the same thing with low temperatures or rain. You know, take all the rainy days over that 30-year period of time and for every single January and figure out how much rain they got or how many rainy days you would expect. And you can average that. And that's what a climate is. So the climate is kind of the average general atmospheric patterns over any given period of time. For us, when we talk about climatology in kind of human terms, when we look at weather records and stuff like that, that's over a 30-year period of time, right? So how has it changed from this 30-year period of time? So like the rain we got a couple weeks ago, right? Two inches of rain in Turlock. Wow, that was, you know, some of the most rain we've gotten. That's way above average. We normally average like an inch. We've got over 2 inches. That is the climate that we're talking about, right? We're comparing it to an average of what we would normally expect. But we can also do climatology with, you know, 1,000-year periods. Like what was it like over a given 1,000 years? And we can go back into the fossil records and ice cores and things like that and piece together what we think the weather was like during those times over a long period of time. We can't go down to a specific day, hour, and time, but we can figure out the climate of those areas based on some of the cool things that we find in the fossil record, which we'll be looking at later on. So another way to kind of separate the difference between weather and climate is what you expect, weather is what you end up getting, right? So we would expect Turlock in January to be, you know, probably the coldest month of the year, probably our rainiest month of the year, things like that. But you know, how cold would it be? Is it going to be below freezing? Well, not really. We wouldn't expect too many freezing days. And we wouldn't expect any like 100-degree days in January either. So that's kind of what we expect. But every once in a while, weird things happen. And that's what we end up getting, right? Is the weather is what we end up getting. So we're going to talk more about next week what can cause a lot of these different things to happen, like uneven heating of the Earth's surface, differential heating between water and land, the rotation of the Earth, all this crazy stuff we're going to get into next week. But the thing I want you to kind of see and to point out right here is that we have a lot of different climates, like 11 different climates within California, where, you know, it might be cooler timberlands up here. We have like what we call an arid steppe, which is basically grasslands down here. Semi-arid means it's much more, you have more water and moisture in it down there like this. Maybe you have Mediterranean climates where you see the blue. And so we'll learn what some of these mean as we go forward. But the big thing that we want to take a look at is, wow, here's like hot and dry. Oh, Bakersfield is the same color as Death Valley. It's basically a low latitude desert. And that's part of the southern part of the valley here is basically on the verge of desertness. It's a semi-arid steppe here. So these are some things to think about and know. And what we're going to do now is try to investigate what are some patterns you see in some of these cities in California and different places in California. And what do we notice about where they are located in terms of mountains versus oceans or things like that. So actually, you know what? Let me see here, 650. Yeah, I'll probably just finish up with this and then we'll finish up with the other climate graphs when we come back after this vacation here. All right. But one thing I just want to show you to begin with, and then give you a heads up of where we're headed, is we can get a good idea of what a place's climate is like by looking at something called a climate graph, which is just a graph that shows the place's climate. And so what I have is a data set from Turlock where we have the average high temperature, and each one of these letters represents a month, right? So like January through December, all the way down through there. And so if we average Turlock's high temperatures in January, our average high temperature would be like 54 degrees. And if I were to plot all of these numbers on this chart, and I use the Fahrenheit temperature gauge on the left-hand side here, this is kind of what I end up with, this data plot, right? Now, if I do the same thing with the low temperature, which I'll do in blue here, well, a gray, I guess, and then I thought I did it in blue, but maybe I didn't. But in gray, put it there like this, that gives us our low temperature. So there's a couple of things that kind of jump out, right? We can tell that, oh, these months of the year are the hottest because the line is highest up right here. And what's also interesting is the temperature differential between high temperature and low temperature. That's a pretty big swing. If you look at it from here, it's like 28-degree difference between high temperatures and low temperatures in July. But if I go to January, the other J month over here, look at that. It's only a 14-degree change between high temperatures and low temperatures. So daytime and low and nighttime lows. So these are some of the things that you can kind of pick out just by looking at the temperatures. And you can see that it never really gets below freezing on average or anything like that. And you know, that gives us a good idea of what we're looking at. Then for precipitation, that's going to be listed over here on the right-hand side of these climate graphs. And so if I say like 2.48 inches, I'd go up 2.48 and then draw my bar graph over here like this. And if I plot all this data, you can see, oops, when the rainy seasons are in an area and how much rain they get. Okay, so I'm going to take you on just instead of doing a breakout room, I'm going to take you on a quick little tour to show you a few differences. And then you guys can note some of those differences down enough for your Jamboards, or not your Jamboards, but your sketch notes here a little bit later on. So these are all different places in California that have different climates. Oops, what the heck? Oh, my family's home. They just came in the front door, I guess. So check this out. If we go in and fly into Death Valley, oops, let me present this. My face is big. Close it down there. There we go. So if we fly into Death Valley, the first thing I notice around here is, holy cow, it's a lot of brown. So that's probably a good indication that maybe there's not much rain or anything like that. And if you look in the bottom right-hand side of my Google Earth, you can see that it's minus 270 feet below sea level. So it's really low and looks pretty brown. And if I click on the climate graph that I've included here, take a look at this. The high temperatures, right? The hot season is obviously still going to be from like April to, you know, October, where the high temperatures are an average of 90 degrees or warmer. And in the summertime, look at that in July, we're talking like 115 degrees is the average high temperature down there, which is just, you know, totally nuts, right? Here's our rain over here, and we can see, ooh, look at that, Death Valley. In no single month does it even ever get on average an inch of rain. And if you were to add all these up together, They basically get like 1.8 inches of rain in a given entire year. That's kind of what Death Valley's climate is. So that might explain if it's really hot and really dry, that might explain some of the brown that we're seeing here. Not much plants can live in such hot, dry environments. And we're going to learn why this is so hot and dry like next week or next class. So if we fly into Visalia here though, right, we take a look at Visalia. It's surrounded by agricultural lands, but I also noticed the hills are kind of brownish and things like that. So maybe that's an indicator of not the most amount of rain. And we know from last week and the few weeks prior that a lot of our agricultural water comes from groundwater or rivers and dams. So they don't necessarily have to be in a wet area in order to get that. But if I click on this, here's our climate graph compared to like Death Valley. Look at that, Visalia still gets pretty hot, but it's not 115 degrees hot. So it's hot, but it's not like world record hot. And we start noticing this pattern again, where it's dry, 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 July and August. And the wetter seasons for these areas are like the winter months, right? November, December, February, and March and January. That's generally when the rain falls. So, it's kind of an interesting pattern. I wonder if that holds up. And I wonder if that amount of rain is normal for a lot of places, right? Well, we can use Crescent City way up here in Northern California to kind of blow this out of the water. If you look at Crescent City, A, it's right on the coast, right? And B, look at it's got these Coast Range mountains all around it, the Klamath Mountains around it, which are kind of this high point of topography. And what's kind of nuts is I notice everything's really green up there. And if you click on here, oh, look at that climate graph, right? Really wet. I mean, some of these months, like December, it gets like 10, 11 inches in 1 month. That's basically what Turlock gets in a year. They get in a month up there. And they have multiple months where they have a lot of this, but the general pattern remains that the drier months are still in the middle of summer for us. But here's the other cool thing. Look at this. The difference in high and low temperature is much more narrow. Notice it never gets really hot in the summertime. So the average high temperature in August is only like 61, 62. The average lows in the summertime are like in the 50s, but it pretty much stays like that year round. Maybe in January, the average high is like 40 and the average or average low was like 40. The average high is like in the mid 50s, but it doesn't matter what time of year you're here. There's no hard freezes. There's no hot times. There's no cold times. And there's a kind of a drier spot in here, but even that dry spot would be a lot of rain for Turlock probably for that entire month. So I just want you to be able to see that we have these different climates. We kind of see these general patterns emerge, but let's take a look. So there's Crescent City. Look at Redding. So if we come inland a little bit more away from the ocean and we kind of fly into Redding here, look at that. That's the Sundial Bridge in Redding, which is pretty awesome. And you can see Mount Shasta from it on a good day here. But if you click on this, look at that, just inland a little bit from Crescent City, and all of a sudden temperatures peak again. So Redding gets a little bit more rain than like Turlock, like 6 inches in December, almost 6 inches in January. But again, that dry pattern emerges in the middle of the summer, hot, pretty mild temperatures, but look at this, right? Still doesn't get below freezing or anything. So the last one I want to show you is like, I just want to compare El Centro with San Diego really fast, and then I'll let you guys go for the evening here. So for El Centro, my tongue's a little dry, so I can't roll my enunciations very good or pronunciations very well right now, but look at all of that farm field down here. All these farm fields. It's one of, part of the bread baskets where our lettuces and stuff are grown in the wintertime down here. Gets water from the Colorado River and some of the canals and aqueducts that come from the Colorado River here. Irrigates all of this. The runoff goes into the Salton Sea. Like, okay, this would be a great place to live, right? And then you click on it. Whew, look at that. What the heck? How does a place that's almost the same amount of rain as Death Valley, how in the heck can they farm down there? And notice, look how hot it is in June and July and August. Whew, look at that, 105 average temperature, so super duper scorching hot. The pattern's a little shifted in the rain though. Look at that. It's dry times is like April, May, and June and July, but it's a little wetter in August and September. And that has to do with what we call monsoonal moisture, influenced from the Gulf of Mexico and also the Gulf of California. Sometimes it flies over to here. But compare this then with San Diego, which is right over here. So just a few, like barely 100 miles away. But now that we're going straight to the coast, right? So remember, here's the hot temperatures here. Let's look at the coast of San Diego. And if I were to fly into San Diego right here like this, here's all the cities and the 3D buildings and all that cool stuff. But look at the climate graph of San Diego. It is a world apart. So when it's 105 over in the middle of, like over by the Salton Sea, just a few 100 miles away in San Diego, it's barely 80 degrees in the summertime. So this is why everybody likes living down there, right? The summer times are not extremely hot. The winter times are not extremely cold. Anytime. I mean, it's, you look at it, it's kind of got a very similar pattern to like Crescent City, except warmer and still drier, right? Definitely not more rain than what you got out in the deserty parts, but definitely not like even as much as Turlock, I don't think. So if you can ship water in, this is why people like living here, is this climate stays pretty consistent all year round. And that consistency again shows up on the area that is near the ocean. So I just want to show you, I lied, I'm going to show you one last one. San Francisco, just to double check and show you here. Look at this. Here's another coastal area, San Francisco. If we fly into it, notice that the temperature swings are much more muted, right? The highs and the lows are very similar no matter the year. And here's that same dry pattern emerge. So we're going to see next week when we come back that it's not like this. This is a very California specific kind of climate patterns, but the proximity to being to the ocean or being far away from the ocean or being up high in the mountains or low in elevation are really going to affect the way things heat up and cool down. And that's going to affect the way air patterns move. That's going to affect then the weather that we get, and that's going to affect the way we can live. All righty. So we'll call that good for tonight. You guys did an excellent job hanging in there. I appreciate it. I hope you have a tremendously rewarding vacation, and I hope you don't have to do too much work or anything like that. And I hope you get a chance to kick back, relax a little bit, enjoy what you can enjoy, assess everything that you need to, and we'll come back strong for the last couple of weeks after that. And I'll see you in 2 weeks. All right. I'll see you in 2 weeks. So have a great vacation, everyone, and I'll see you later.
You'll be available through email, right?
Yep, email, I'll be checking. And then, so the office hour dealy bobs, if you want that, I'll do my best to reply to you. I wouldn't expect, like after Tuesday, I wouldn't expect much email checking because I'll be out and around on holiday and things. But yeah, before Tuesday, definitely I'll be around. So, and then once we come back from holiday, I'll have more frequent email checking. Yep. So.
Okay, thank you.
All right. Have a great night, everybody. See you later.